This is a talk, like an unoptimized talk, not knowing any real algorithms. I want to be able to move around a playing field. This came out of a coding challenge that I was in over the last couple weeks, a couple minor problems, and a couple of the problems actually turned out to be solved in a similar fashion. One of these I'll go deeper into another time, but basically the question is, I have two problems. What are all the squares I can visit in an exact number of steps, and what are all the locations I could end up in after an exact number of steps? And those two seem to overlap. And the way we're going to do this is I'm just going to post all the possible moves from any given square to a task list. And then for each one of those squares I could move to, I am going to evaluate it. All the squares that I could move to from that one, I'm going to post those to tasks. And every time I move to a square, I'm going to close the tasks that put me on that square. And then I'm going to use those two lists, the closed list and the open list, in order to not repeat where I was before. So basically, I'm pruning out previous moves to make this work. And actually, it's a little interesting for one of these, but I thought it was interesting for both. So open tasks, it turns out, if I post moves I want to do and I do it in a FIFO, that means I pull the first ones out, posted first, and process them. That becomes a breadth first search, a breadth first movement. That means I would move out from the center. If I do a LIFO, I actually pull the last task that I did and find all the locations to move off of that, and then I put one of those. And that's a drill down, a depth first. And so in that case, if I'm sitting somewhere, you'll see it move off in a fashion, in a branching fashion. It'll go down one branch and it'll do all the leaves on that branch. So in this case, I ended up doing FIFO. Turned out there were reasons for that because we were doing like 100 million moves, and I wanted to be able to prune a couple of these. So one of the things that I implemented these tasks in Dart, I did all this in Dart, and it turned out the set was actually faster than the list, 20 times faster than the list. So be cognizant of the data structure you use. Man, it was a huge 20 times. It's like a big difference. So let's talk about the problem we're in. The problem we're in is a playing field. And if I'm going to visit, what could I visit after 4 steps? And if I only move in one direction, that would be 5 squares. So if we did step 1, step 2, step 3, step 4, moving from left to right. So I'm just lit up those. That's just like, what did I light up? What square was I allowed to visit with a certain number of tasks? And the parallel problem I'm really going to solve using basically the same technique with one difference is, what squares after exactly 4 steps would I end up in, moving left to right? And so it turns out I can go 4 steps out, or I can go 2 steps out, and then back 1, and then back forward again 1. And so pretty much every even number square away from me is where I can end up on one of these. Well, I guess if it's a 3, it would. Yeah, well, it's the multiple. You know what? Forget it. I didn't say that. But basically, you can see that there'll be empty spaces, and we have the ability to move back a couple spaces and move forward depending on, how many steps we're talking about. So if you want to see how this would fill out completely, I showed you the one just moving to the right before. The one on the left is all the squares I can light up in 4 steps. And the one on the right is all the places I can end up after 4 steps. And because it's an even number, we end up on every even number square. And if it's not a number, you'd end up with something different. I didn't draw that one up. So if we simplify this and we look at 2 steps, right, on the left-hand side, we see that there are 4, because you can move in east, west, north, south. You can move, the first step is always gives you 4 spaces. Every one after that, it all depends, also does east, west, north, south. And we're pinned on the left-hand side, so it's a little asymmetrical on that side, but on the right-hand side, you can see that not only we got 4 on the first one, when we move to the S1 to the right, we actually get 3 more. So basically, every time we move to a square we haven't been to together, we might get 3 more. The playing field on the right is basically exactly after 2 steps. Those are the ones we would end up on. So this is the shrunk version of the 4-stepper. And then I'm just going to show you how this is going to work with a task list. So no place for my head in this video. All right, so we're going to start on 3-1. So we have an open task in square 3-1. That's this one right here with the blue on it. We're going to process that task and move it to the completed task. When we're on 3-1, it turns out there are 4 squares that I can move to off of that. And so each one of those gets posted as a task to the open task list. It emptied when I move here, and when I leave, when I'm getting ready to move off this square, I actually have 4 squares I can move to. I have since I started on 3, 1, I can go to 4, 1, 2, 1, 3, 0, and 3, 2, right? So those are the 4 squares next to me because I can't move on diagonals. This would work just as well with diagonals. If you were pretending these were like, well, that won't work, hexagons. That would be something different. So when I'm done processing square 3, 1 here, I have 1 completed task, which is 3, 1, and I have 4 open tasks. If I go to the 4, 1 square, row 4, column 1, the one right below it, there are 4 squares next to it. So I could post 4 more new tasks, but it turns out one of those is one I've already completed, which is 3, 1, so I have to skip it. So when I leave square, when I'm done processing 4, 1, I still have 3 tasks open for the first square, and now I have 3 tasks open for the second square. The first one had 4, the second one had 4, but one was a dupe, so now I'm down to 3. So, and we processed the square we were on, so we posted 4, we posted 3, we processed 1, and so we end up with 6 left when we leave it. If we do breadth first, we're going to pick up one of the other first steps off of this. We're going to pick up 2, 1 here. That'll put the 2, 1 on the completed task list. We'll end up with 2 of the original first step squares not processed yet. And then the new square that we've got, which one did I pick? Row 2, column 1. Yeah, I picked the right one. That one also adds 3. So we ended up with 3 from the first step, and we ended up with 3 from step 4, 1 going down, and we ended up with 3 from step 2, 1 going up. So these guys are all adding more. And if we were to do one of these side ones, these 2 would have already been processed, so we won't add 3 every time. And basically, we just dropped 1 here because it had already been processed, so we end up with 8 more squares to look at, and we end up with 3 of them already processed, and so we would go through 3, 0 and 3, 2, and that would probably give us another, it wouldn't give us another 6, it would probably give us another couple, though, and then we would move through that. And so that's how this works. We basically look at all the legal moves, and I use that explicitly here because some of the, I'll show you one in a minute, and then those legal moves are posted as future moves. Now, if it's exactly 2 steps, I made a change in this. You can see that we still have a step with the row and column in it. So we start on 3, 1. You know what? Let me make that. Oh, man. 3, 1, right? But I also include the step count. Why is that? Because the dupes, when we're only looking at where we end up, I can go back to a square and come forward again. But that would be a different step count. So the previous one was everything that's lit up, don't care how many steps. This one is how many are lit up, how many places can I get to an exact number of steps. So what we'll do is in the uniqueness, it's not just the step that has to be a dupe, it's actually the step count. So square 3, 1 with 0 in the 0th step and step 3, 1 in the 3rd step are actually 2 different things. And so those aren't really dupes of each other because in this one here, we're trying to figure out in exactly how many steps, where could we end up? And so the step number we're in matters. In the one we did up here, the step number didn't matter because we were just trying to figure out how we could light stuff up. And so everybody that was a dupe, actually, we needed to remove. And here, a duplicate takes into account the step you're on. And so this table lets you run through that. The only other thing I wanted to cover, I got just a minute here, is it turned out in the problems, some of these are blocked. And so we still do this the same way. If we start on 3, 1, we look into 3, 1, we've got 4 squares around it, right? Step 4, 1, which is down, is actually blocked by an X, so we're not going to add it to the list. Step 2, 1, moving up is okay. Moving to the left, I can't move to the left because we have another block, so that one doesn't get added. And then 3 to the right is open. So when we leave the 3, 1 square this time, instead of having 4 squares, 2 of these were blocked. We only end up with 2 on the active list. The same thing happens when we move from row 2, 1. So we move up 1. And it turns out, if you look at it, 3 of the squares are blocked, 2 of them by an X, and 2 because we've already been there. And so we can only post 1 item to the task list, right? That's all we end up with. And so we move through this way, right? We basically just, for every square we get, we say, what squares can I legally move to? And then using the right hash algorithm for uniqueness, whether it includes steps or not, we end up with a set of all the ones we've completed, and that'll tell us how many we lit up. And if we did it on the one before where we included the steps, it'll tell us how many steps it took we could get there in, right? And so we would do the same thing for this one. I'm out of time, so we'll cover it another time. Have a great day. I hope this gives you an idea. If you're stuck in like a playing field kind of thing and you want to move around, this gives you a way to do this with for FIFOs and LIFOs if you want to do breadth first and depth first using open tasks and closed tasks to make that work. Have a great day.